So thank you so much for joining. This is the Exploratory Online Seminar number 83. Today, I like to do what I like to do is introducing the hypothesis testing. This is kind of like introduction stuff. So we are now going to go into the detail part of the hypothesis testing. We are now going to introduce like a particular type of hypothesis testing. This is more like kind of setting up the foundation. And then I'm planning to do, other follow-up sessions for, introducing hypothesis testing like t-test, ANOVA, and a chi-square, and so on. So those will come, after next week. But today is a sort of a basic idea of like hypothesis testing, like why we do this, how that works, how we should think about this thing, that type of things. Okay, so. Let me introduce myself. My name is Kaan Nishida, CEO at Exploratory. We started Exploratory 2016 to democratize data science by building a tool called Exploratory. And also we do this type of seminar and a training to share our knowledge and skills so that we have more people know the data science or can use the data science. Our vision is data-informed decision-making is the key to make the world better. Therefore, our mission is to democratize data science, and so everything we do is always around this mission. When we think about data science, it's usually like data access, data wrangling, visualization, analytics, communication. These are the 5 key components to do any type of data science project. So we build Exploratory to make these tasks in a consistent, sort of like a streamlined, consistent manner to by providing more than simple UI to make these things easier and more effective. Okay, so let's get into the main thing of the day. Exploratory Online Seminar number 83. Introduction to hypothesis testing. So today's agenda, we got a lot of things today. I hope we can finish it in the 60 minutes. I'd like to start from decision making and all the way to hypothesis test, and then eventually the p-value and significant level. If you might have heard or studied hypothesis testing in a textbook or classes before, this seminar is going to be a little bit different. Usually, like hypothesis testing, you go into like null hypothesis and p-value, but I'm gonna kind of like go step by step so that you guys can see like why we have to talk about null hypothesis, why we have to talk about this like a p-value and a significant level kind of stuff. So with that in our mind, let's get started. So decision making. By the way, last week I did a probability seminar, Introduction to Probability. And at the end of the seminar, I talk about like how we can use probability in sort of like decision-making process. And at that time, I actually touched upon this particular scenario of wine tasting. So when you go to the party, whatever the party that could be, there's always the people like tell you like he or she knows the difference about wine. They know about the wines. So this guy I met told me he knows the difference between French and California wine. So, so like I would be like, really? Are you sure? Okay. Or maybe like he's bluffing. He's just saying it because there are a bunch of other people. He wants to be liked by others and stuff. Or maybe he knows what he's talking about. So what we're going to do? Well, let's do the blind tasting. It's kind of hard to do this kind of stuff at the party, but let's imagine we can. So what we're going to do is we're going to prepare, maybe the 10 glasses or 20 glasses, whatever that could be. And then we pour California or French wines randomly. So nobody knows, especially the people who we are going to test. And then there's no label. All things that he can see is the glasses and the color. Maybe color might have a difference. No, I don't think so. So you have to taste it. If you know it, then you can tell like, hey, this is California French wine, right? So after we did the test, and he was correct for 6 out of 10. And at that point, we're gonna have like a bunch of different opinions. Maybe you might say, hey, he was correct more than wrong, right? 6 versus 4. So he must know the difference. Or maybe another person said it's almost half and half, 6 and 4. What's the difference? It's just a coincidence. So then like this kind of conversation goes probably nowhere. No, because nowhere, like we don't know like how we can conclude this thing. Like how are we gonna decide, like, you know, he knows it or he doesn't know. We can keep talking about it, especially with the wine, drinking wine. So here I like to introduce the two way of thinking. I'm sure like you might have heard about it or before, and it's kind of like obvious for some people, but I just want to make sure like everybody knows it. So deduction and induction, or deductive reasoning or inductive reasoning. Okay, so deduction or inductive reasoning, deductive reasoning is basically you have some kind of like truth, or at least like you have sort of like established truth or assumption that everybody would agree. Okay, and from there you actually use logical thinking. You use a logic, and then leads to the conclusion. So the conclusion at the left-hand side at the bottom you get is logically correct, right? So like you make sure like everything like kind of like logically correct. So, and then you start with a truth, or like something that everybody thinks is, I agree, then the conclusion must be true. Right. So these types of things, it can be, you can say logical thinking or rationalism or whatever you want to call it. But the point is these types of thinking is a deductive reasoning or thinking. And that was defined like way long ago. It's like, even the BC in Greece. And there was a guy called Aristotle, and he wrote a book called Organon. And in that book, he defined this type of a deductive reasoning process as a sort of like a logical argument. Okay, so like I said, like by using this, you can reach the conclusion based on logic and universally established truths. Okay, so for example, let's say like you have like all men are mortal, and then probably most people agree, and Aristotle is a man as long as we know. Right. So that case, then Aristotle will die because 1 and 2 are correct or is true. Therefore, logically conclusion at the bottom must be true. Okay. So that's a deductive reasoning or deduction. Okay. And the history of science, most people actually get confused. It's like science, the word was introduced after like 17th century, around the time like Galileo Galilei or Francis Bacon, or whatever the modern science started flourishing. So before, we used to call natural philosophy or mathematics or whatever the name that could be. But anyway, so after the Aristotle, there was a 2,000 years pass, and eventually something new started coming up. And at that time, this guy is not a scientist. He's more like a philosopher or politician. But he wrote that book, and then in that book, he basically argued for the possibility of scientific knowledge based on only upon inductive reasoning and careful observation of events in nature. And in that book, he basically criticized the deductive reasoning, the one that we just talked about, is defined by Aristotle in Organum. I think that's a Latin, I don't know, Latin or Greek. I mean, Aristotle, the Greek guy. So, but I'm not sure this Organum itself is Greek or Latin. Sorry for my limited knowledge. But anyway, so Francis Bacon wrote a book, Novum Organum, right? So because to criticize or kind of argue against the Aristotle. But Francis Bacon endorsed a new way of thinking with the inductive reasoning to advance our knowledge. And this becomes the foundation of scientific method later. So here's Galileo Galilei. He is a scientist. He's not a philosopher or a politician. He is a guy who actually practiced the science, right? So he is usually considered as a father of modern science. But most importantly, he established a scientific method, or he actually practiced, or he actually used it when he proved many things I'm going to touch in later. But that method is he tested the hypothesis through experiments in the real world or through observation. So one of the main achievements is obviously this heliocentric theory, which is basically the sun is actually the center, not the Earth. Because until then, the common knowledge was Earth was center, and everything's kind of like around surrounding Earth. But then he actually went against it. He was not the one came up with the idea, but he actually proved it. How? Well, first of all, he created this telescope. And then by using this telescope, he observed many things. And one of them is the sun. And then he's not just a sun, he was actually observing a black dot on the sun. And then not just observing, he actually recorded it. And then he basically collected today's world, the data. So, right, so every day. And then eventually he discovered this actually black dots are just not happening randomly. It actually moves. And then that itself telling us that sun is rotating. And that means the Earth can rotate too. And then he observed other things as well, obviously. But this is one of them that actually helped him to experiment and prove that his hypothesis, which is that actually the sun is the center, not the Earth. So what happened is that inductive reasoning, he basically observed and then eventually concluded the theory, which is the sun is the center and the Earth or everything else is surrounding it in that sun. And this type of thing is called empiricism, because based on like experience or observation. But in the world of Silicon Valley, we call it tested. Right, so it doesn't have to be Silicon Valley, but today's world, just test it and then make sure like if that's true or not. Test it means it's not like testing the laboratory, testing in the real world with the customers or with users and so on. So to sum up, deduction, induction, these two things are kind of like opposite of the things. So the direction is different. So deduction is something, the truth is already there. And then from there, you use the logic to reach the conclusion. Okay, therefore, you can explain what's happening in the real world based on this conclusion. You can even explain why this is happening, kind of stuff. But the right-hand side induction, the direction is the opposite. The real world is the first, and you observe. And then by using the probability, I mean, I'm not sure they used to call it probability, or generalize what you see, and then try to estimate that generalized truth. So these truths never be the 100% true. That's why like I use the word probability here, because you based on the observation. So you might not seeing something that you are not even aware of. So therefore, the theory is not the true universal truth, might not be the truth, but as of that moment, it most likely kind of truth. So that's generalized truth or theory. Okay, so that part, this deduction, induction, this difference is very important before getting into hypothesis testing. And also, I'd like to also touch base on the scientific method. So scientific method, I'm sure like you have heard of it, but I just want to, again, kind of clarify or just set the kind of foundation on this one. So great physicist, Nobel Prize winning physicist, Richard Feynman. I love this person, and he wrote many books about the science, and then his way of writing is just always so entertaining, but also there's some really practical, useful meaning in his books. And then also you can find his YouTube video when he explains science or when he explains physics or whatever the universe. It's always so simple and it's so entertaining and it's so insightful. But anyway, so one of the actually, you can find this video as well, Scientific Method by Richard Feynman. He said that these three things, the scientific method is super simple. First, you guess, and this is basically like in our language, the hypothesis. And then you predict. So if the guess or hypothesis is right, and what can happen, like you predict, usually you compute or like use math or whatever to estimate or predict what's going to happen, right? And then that part is done, then like what do? You do the experiment, basically test it. And then make sure, well, that's how to make sure, but you just compare between what you predicted and what really happened in the real world. It sounds like kind of like a deductive reasoning, inductive reasoning, kind of like a getting here. Maybe you can guess. Okay, so here's a scientific method. Like this is more like a typical scientific method you might see. So you start with a question, and then you hypothesize. This is according to Richard Feynman. It's more like a guess, and then you predict if the hypothesis is correct and what that world is going to look like. And then you test in the real world, and then as you study. The study part is basically like a compare between what you predicted and what is happening, and those are consistent, inconsistent. If the consistent, meaning what you predicted actually is really happening in the real world, then you accept the hypothesis. And then if you that is robust enough, then you can develop the theory. That's the theory that it's actually, I was talking about the inductive reasoning side of things. Okay, but if it's not consistent, meaning inconsistent hypothesis, you predicted something and then that's not happening in the real world, obviously you want to reject the hypothesis. And then usually like you can, it doesn't have end here. You usually, there might be something wrong in the test, and then so you kind of going back and forth at some parts, but this is basically in a kind of nutshell of the scientific method. And then Richard Feynman said, if we disagrees with it, it's wrong. So what that means? So if what you predicted is not happening in the real world, then that's wrong. So like that, what is wrong? That hypothesis is wrong, right? And then so deduction and induction. So in this scientific method, basically the hypothesis to predict, that part is deduction. You just estimate, you're just kind of guessing. So logically, probably correct, right? So like based on the hypothesis, this might happen. Whatever the model you use or the calculation you use or like any logical logic you use, whatever that could be, but that part is in a kind of like in your head or more like a theory. And then induction side, you actually go out the world and then see, observe, experiment, and then see like what that is really happening or not. Okay. So this is like a deductive, inductive. It's not just one is better or not, but it typically, like as you see in the scientific method, it can be used together. And then that's not just scientific method. That sounds like kind of like a fancy word, but it's actually, we do this every day. The great statistician from UK called George Box, he said, science is a means whereby learning is achieved, not by theoretical speculation, nor by the undirected accumulation of practical facts. This is part basically not just deduction, not just induction, but rather by a motivated iteration between theory and practice. I think this is beautifully put together, the whole scientific method, and which is, he calls it iterative learning process. Basically, in order to acquire new knowledge or advance our knowledge, then typically we actually go back and forth between induction and deduction. Or upper side is like a data. This is real world, right? So like the facts and the data and the phenomena or whatever. And then the bottom side is the thinking in your head, which is like theory, hypothesis, and a model. And then not just one of them is better than the other, or just one of them can be enough. It's just, we need these two going back and forth. So let's think about like one scenario. Where is my car? Right, so like you go to the parking lot and then you're trying to find your car. You can't find your car, and you start kind of like sweating. So what's happening in this kind of like induction world? You observe, and your car is not there, and then where it's supposed to be, and you estimate what happened, right? So what happened? Maybe like you might say, someone stole my car, right? And is that true? Then that's where the deductive thinking start coming in your head. If that is true, if my car was stolen, that is a hypothesis. That's not definitive, right? Like you're still guessing. So it's a hypothesis. Then use the logic to conclude what can happen, what is the world would be. So if my car was stolen, maybe like my car should not be in the parking lot. Sorry, not even maybe. It should not be in the parking lot, right? Well, maybe like, this person like returned the car, maybe there's such case. But in general, the car should not be there in the parking lot at all. right? So like what we did is using that logic, we defined the expected outcome that can be logically concluded if the hypothesis was correct. And this again it's happening only in your head. What you should do is like you should open your eyes and observe, right? And we call it test in a scientific method, or even the language of the Silicon Valley or a web company or whatever. So we observe in the real world, and then like you walk around, and then it turned out the car was parked at a different spot, way different spot, but still in a parking lot, same parking lot. So what you did is that you try to compare with what you observe in the real world against what you estimated. And then what you're going to do is basically you study. So now you have to decide, like, hey, this is consistent with my hypothesis or not. Your hypothesis was your car was stolen, but the world of reality, I mean, if the car was stolen, then the car shouldn't be in the parking lot. But the world of reality, the car is in the parking lot. So these two things are not consistent. It's actually inconsistent. So what should we do? Okay, so that means the hypothesis is not working. That's not really helping me, right? It's not like it's giving me the inconsistent result. So we reject the hypothesis. This part is the important part of the whole hypothesis testing I'm going to talk about in minutes. Okay, you reject the hypothesis. Then the conclusion can be the opposite. Well, my car was not stolen. Okay. Then, like George Box said, what we usually do is we iterate, right? We don't stop here. Oh, my car was not stolen. Whew, so okay, like I'm going to work. No, you're gonna start. You gotta keep thinking to find out what happened, right? So then you guess based on what you observe, which is like my car was parked at a different spot in the same parking lot. So what happened? Well, one thing I can think of is someone who has the key might have moved the car, and that could be my wife or your husband, your kids, or whoever, right? Then that again, still not the definitive answer, definitive conclusion, definitive truth, right? So what you do is that take that as a hypothesis. So maybe like my wife used the car, and in that case, using the logic, what would happen? If that is the case, what would happen? Then, if she used the car without telling me, then that she must have left the memo in the car. I mean, today, like probably like, I would appreciate the memo better than a text message, but, I might have missed a text message or something, right? And then test it. Let's check it. I think it's more appropriate. Then like you found the memo in the car, or you found the text message that you haven't even checked or whatever. So what you did is basically testing by comparing what you observed with what you predicted. And then in this case, it's consistent. Consistency between left-hand side or deductive world, which is a world of theory, right? And world of reality in the right-hand side. Those two things are consistent. So that means whatever the conclusion that you came up with based on the deductive reasoning can explain what's happening you see in the real world. So therefore, you can keep accepting the hypothesis, which is my wife used the car. So therefore, the right-hand side top, the conclusion could be that my wife used my car and moved the car. Okay, now case closed, and I'm going to go to work or whatever, right? So, okay, so that's the iterative learning process. Like you saw, it's basically going back and forth, induction, deduction, again and again. This one was super simple, but again, this is what the scientific method really is, but at the same time, even if like you don't do the science or something, but you do it, in almost like every day. I mean, at least I hope you do it. Okay, so that's an iterative learning process. And it's hypothesis testing I'm going to talk about is really very similar to this. Okay, so the hypothesis test is, again, this guy came to me and he said, I can tell the difference between French and California wine. Okay, so let's do the blind testing. Okay, I got the 10 wines without label. So bring it back to the deduction, induction, that framework, okay, iterative learning process framework. So the hypothesis is he knows the why, okay? And if he knows the why, then the conclusion would be obviously like he can answer it correctly. Then we did a test and then he scored 8 out of 10. He was correct on 8 wines and then wrong on 2 wines. So one person came up and said he was correct for 8 wines. Hey, that is something happening. And another one was like, well, that can happen if he's randomly guessed. Like maybe like just a luck. How about like 6 wine was correct and 4 wine was wrong? Well, the first person still said he was correct for 6 wine. That's more than like more correct than more wrong. And another person is like, well, that can happen even if he's randomly guessed. What if like 4 wines are correct and 6 wines are wrong? Well, he was correct for 4 wines. That's something special. If he doesn't know, like he could be like just a 2 and then 8 were wrong. Well, that can happen if even if he's randomly guessed, right? And also you can even argue maybe like he kind of got confused which the French and then the California. He thought he was somehow labeling the wrong way. So in that sense, maybe he was actually correct with 6 wines and 4 wine was wrong or something. And then this again is, hey, we are doing hypothesis testing. Are we not like inductive, deductive thing? Like that's not helping us. What is going on? Well, hypothesis we wanted to prove what he knows about the wines, right? He knows about the difference between the French and the California wine. But here's a problem. So what do we mean by he knows the difference? How do we define knows the difference? Like, does that mean like has to be correct all the time, or he can be correct most of the time? Maybe because in the world of wine, maybe it's not that possible to be correct all the time. Or maybe like once in a while, correct is even okay. Maybe that he can, depends what wine he takes. So how we define, and that's the problem. So at this point, so we try to do the hypothesis test. We're testing the hypothesis, right? But it seems like we are not going anywhere. So that's where the null hypothesis comes in. And to understand, there's a philosopher called science philosopher, I think, in Karl Popper. This one, sorry, that is wrong. This is wrong. Sorry about that. He's not that old. He's actually relatively recent. I think he's already died, but probably like between like before the World War II to probably like 1980 or something like that. But anyway, he wrote this book called The Logic of Scientific Discovery. And in there, he argued the falsifiability as a center for a factor for a statement or theory or hypothesis for disproving it with evidence. So in order to gain the new knowledge or advance our knowledge, you need to do the hypothesis testing. However, that hypothesis has to be falsifiable. So hypothesis obviously, like in the world of statistics, so if you're going to do the science, then it has to be measurable, right? It's not about the feeling. It has to be measurable, called measures. And it has to be testable. And so far we have done that, but it has to be falsifiable. That's the part we're missing at this point. So we need a hypothesis that we can falsify or prove it to be wrong with a clear criteria that is objective and measurable, not by subjective and feeling, obviously. So that says right now he knows about the wines. This hypothesis is a tricky one because we don't know how to falsify this. Like what is the criteria that we can say that he knows the wine? It's like 8 out of 10 or 7 out of 10, 5 out of 10. Like we are not sure like what this means really. And then the problem is this case is wine, but most of things in the world to prove that he knows something or there is an effect if you do the A/B testing or whatever, or if you have the drug or whatever, you prove that has effect or there's a difference or whatever that could be is actually easy if you have the strong will to prove it, because there's always something that you can look for. So the problem is, it's like what degree of the things that we are talking about. So it's very hard to set the criteria to say there's a, we can prove that, we can endorse the hypothesis or we can reject the hypothesis. So what we can do is actually we can kind of flip this thing so that here, hypothesis that is falsifiable, he doesn't know the wine. And this he doesn't know the wine is like basically he doesn't know anything about it. It's basically the zero or something like that. Well, it's not zero because he can randomly guess, right? But this randomly guess means we can bring in the probability. Just like as if you flip in the coins and then it's, predict what's going to happen, head or tail. And then that is basically 50%, right? So that case, maybe this wine thing too is just if these are, randomly ordered, randomly placed, then just a matter of the coin flipping. It's like a 50% chance to be right or wrong on each glass. And at this point, we now have the criteria because the answer will be correct 50% of the time. That means if you have 10 wines, you'll be correct for 5 out of 10. So that part, that criteria part is still kind of like are you sure? Like it's always a 50%, but that just to take the rest for now. But sum this up though, what we have done so far is this hypothesis that is falsifiable. That is called null hypothesis. But null hypothesis, the name as the name indicates, the null is like nothing. It's like an empty, right? So it's all zero or basically nothing there. So usually in any, as far as I know, the hypothesis testing is always have this null hypothesis. And the null hypothesis means nothing. It's like a zero or no variance or nothing. And then another one, or most of the time, the original hypothesis that originally you wanted to prove is called alternative hypothesis. That word is kind of weird, but I'm just using the word, language in the statistics. But basically, like this hypothesis you wanted to originally prove, and hypothesis that you want to falsify, or you should be able to falsify. Okay, and it's a null alternative hypothesis and null hypothesis. And then in the world of hypothesis testing, the null hypothesis is the important one. Even though like you don't know the word called alternative hypothesis, that is fine. But null hypothesis, that word shows up again and again. Okay. So going back to the iterative learning process. So the left-hand side deduction word and the right-hand side induction word. So in the left-hand side deduction word, you start with the hypothesis. He doesn't know the wine. Did you notice? I changed it. Originally, he knows the wine, but I changed it so that we can prove it wrong or falsifiable hypothesis. And from there, logical conclusion could be it would be as good as someone who would randomly guess. If he I'm not sure about this particular person, but another person who doesn't know at all and they just randomly guess, and probably like it's gonna be the around the 50% thing. And then this particular person we are testing right now would be the same. But here's the one problem, right? Because as I said in the introduction to probability seminar, the probability doesn't predict what will happen next in the real world. Okay, so if you flip the coins 10 times, you might get only 3 heads out of 10 flips. Or sometimes you get 3 heads out of 10. You might get 7 heads, or you might get all heads out of 10. But in the world of probability, there's something called law of large number. If you repeat over and over again, they eventually settles down to the theoretical probability, in this case, 0.5 or 50%. So now we have the model on the left-hand side, which is basically the probability to be correct is 0.5 or 50%. In this particular case of the wine casing, it's either the California French wines. Okay, then we have the model left-hand side, and then we expect to be 50% of correct. And if we repeat the test with random guess, which is that model we are talking about, again and again, over and over, what is going to happen? So let's kind of simulate this. So first time, maybe like he randomly guess. It's like this wine glass, but you can do the same thing with the coin flipping, right? So like first time you have 10 chances, and then how many times you're correct. And in this case, 8 times you're correct. And then second time, like 5 times correct. And then right-hand side, I started putting the block as a sort of histogram or bar chart. Okay, and then being correct, x-axis being correct. So right now at the position of 5 and 8, I have 1, 1. And the third time, like I got 3 times out of 10. This is like a random guess, okay, or random coin flip. And then like tested 4th time, 5th time, and 10th time. At this point, I've already got 3 times being correct for the 3 times. Okay, and then 20th time, and then like you start seeing like the little bit, not just a flat, there's some kind of like a pattern start emerging. And I did it 50 times, I did 100 times. If you do this test with wine, I don't recommend it. Make sure you don't do it. I don't, it's not, I'm not trying to make you guys drink, but by this time, probably you're in the bathroom. But besides that, like 100 times, looks like some kind of like what do you call it, normal distribution-ish, symmetric kind of bar start emerging. And then 100th time, definitely you are already in the hospital. But at this point, though, notice that like that the center of this chart is a 5. Right, and when you think about it, if it's like a random guess and like random like coin flip, like then you should have 50% of the chance you're correct. So therefore, like it's probably like 5 times correct or 5 times heads is the most sort of like a frequent pattern like you should expect. So 5 out of 10, you're correct. Okay, and then sometimes you might be correct for 9 out of 10. You might be correct 3 out of 10, but 5 is the most likely, and sometimes 4 and 6. That's also can happen a lot. Okay, and then if we repeat, basically, if we repeat this experiment over and over and over, it will end up with this, it says asymmetric. This is actually symmetric, right? Like a right-hand side, left-hand side, basically is exactly should be the same. Okay. So, and this type of probability distribution, this type of thing called probability distribution, the reason probability is sort of a kind of ratio, but it's basically like what is the chance of like you getting 5, what do you get the chance you getting 4. So that's why we call it probability distribution. And particularly this particular case is called binomial distribution. There's a bunch of other probability distribution, but in this particular case, okay. But the point here is not really about the binomial distribution. The point here is once we know this we can get the binomial distribution for things like a coin flip, for things like a random guess of the out of 2 choices, then you can use this, then start talking the probability language. So now here is a deduction. We got so much progress actually on left-hand side. So we started with hypothesis. You remember that is falsifiable hypothesis, which is he doesn't know the wines. And then from there, they logically reached the conclusion, which is it might not be exactly 50% because probability is probability, right? But it will be somewhere that can be explained by probability distribution. This particular case is binomial distribution. So that means maybe like it might not be 5, right? 5 out of 10, but maybe like a 6 or 4. But that also can happen in a higher chance, right? As you have seen in that symmetric chart, bar chart. Okay, so once we set that left-hand side, then we test it in the observation phase, and we compare with what you observe in the real world. Right. So, or left-hand side, we have the model, which is 50%, just probability model. And the right-hand side, we still don't know how, this person is going to perform. we kind of know, but let's pretend we don't know. Then let the blind testing begin, or let's collect data in more like a data science world. So we did the test, and he was correct 9 times out of 10. Wow. So, but what that means is like that, it's like, hey, like the probability is probability. Like maybe that can happen. Well, how often does something like this happen? Well, in order to be correct 10 times out of 10, is 0.01%. That particular part, the right-hand side in red, you can slightly see at the bottom. That's actually 0.01% of entire area. Okay, so that's 0.01%. So that's probably like not gonna happen. It's almost like unlikely, right? But he was 9 times correct. So what that means, so he's correct 9, and maybe like he could be like 9 times correct or even more, including 10. So from 9 to 10 is actually 1.07%. In order to get there, there's only 1 in 100 chance, right? 1.07%. And this particular percentage or the probability is called p-value. In this case, 1.07%. P-values, P stands for probability, literally. But in this case, in this particular case, is that if the hypothesis, that remember the null hypothesis, which is basically he's guessing randomly, right? So if that null hypothesis is correct, then whatever the value, whatever the result you're getting, what's the percentage? What's the probability of that? That is the p-value. So in this case, we observed, and what's happening, he was correct 9 out of 10, which can happen, but only 1% of the chance, 1.07% of the chance. If we accept that he doesn't know the why, that means left-hand side top. If we had this null hypothesis, which is falsifiable hypothesis, he doesn't know the why. That means we can assume that he's just doing a coin flipping, the same thing. Then he's correct 9 out of 10. That can happen, but happen only 1% of the chance. And do you think that hypothesis still can explain what we are seeing here? No, I don't think so. Because world of theory, left-hand side, and the world of reality, which is basically this test result, are not consistent. Left-hand side is not helping what's happening in the right-hand side or the world of reality. So if it's inconsistent, that means the hypothesis, that's something to start with, something's wrong, so that we can reject the hypothesis. And then the conclusion is the alternative hypothesis, which is he knows about the wine. Okay, so that's that kind of like a very simple way of drawing the hypothesis testing framework. So now what we have done is that model is not explaining what is happening in the real world with this particular person. Okay. And the model left-hand side is that basically in this case, we use a probability distribution, in particularly the binomial distribution. And then even using that, even we accept that, hey, data values, right? It's not like a probability is always 50%. Well, we accept that can be 40%, can be 60%. Like we can be like 4 out of 10 is correct or 6 out of 10 is correct. We accept that, but still being correct 9 out of 10 cannot happen with random guess. I mean, 1% of the chance can happen. So the model doesn't fit the reality. So we can reject the model or null hypothesis, which this model was built on. But what if he was correct 8 out of 10? So far we saw he was correct 9 out of 10. What if 8 out of 10? And then same thing, we use that same probability distribution. What's the percent of the 8? Sorry, this is actually wrong as well. Sorry about that. This should be 8. Okay, so 8 out of 10. Sorry, 8 out of 10. So in this case, more precisely, 8 or more times correct out of 10. So that can be 8, 9, 10, right? And in that case, that is 5.47%, which is a p-value is 5.47%. Okay, so that how should we take this 5% or 5% thing? And that's the problem here is what is the threshold between hardly happen or can happen, right? So if it's a 5% is okay, or like maybe like a 10% is okay, because at the beginning, like it was 1%. So was it 1%, 0.1%? I forgot, but it was like something like 1%. Like we can easily say, hey, that's not gonna happen. That's not not supposed to happen. So it's easy to reject the null hypothesis. But what if like it's a 5% or 10% or 15% or something like that? Like, is that like a reasonable or consistent or not consistent? How can we decide? And that's actually the very weird part about in this hypothesis testing is, so we have to decide this thing called significant level. And there's no objective logic behind, but there are a few threshold standards of p-value. This is like widely used in the world of science, in the world of statistics. Typically like 5%, 1%, sometimes 0.1%. But to be honest, I've seen like some folks using, for example, the world of marketing. Some people use 10%, 15%. Really depends. Like this is where like you got to bring the domain knowledge, because especially like when you're dealing with the people are not reliable. Like humans are not reliable. So it's actually like if even like that, like your customers or like your users, whatever, like showing like a 10% or 15% chance, that's actually the big thing, significant. And that's actually, you can see that as a signal. But if you're dealing with, for example, car automaker or like some kind of the world of physics, it's more like manufacturing or something, then the 0.1 or even sometimes 0.01%, because it shouldn't be much difference in the usual. So depends like where you are, like what type of data you're dealing with. But in general, and most of the textbook give you this percentage, and especially like a 5% or something. So but here's one more important thing is, this is something that you should decide before you do this kind of testing. Instead of like you do the testing first, and then you come up with like, you know what, like I heard about like is a 5% is okay, or 1% has to be 1%. You can't kind of do that kind of cheating, right? So that you have to decide first, this significant level first, then do the hypothesis testing, and then see the result and then reach the conclusion. But let's say like we generally take the 5% as a significant level, right? And then what that means, then we can decide that any data with p-values less than 5% will be significant. And therefore, we can reject the null hypothesis. But on the other hand, if the data with the p-values greater than 5%, then it would be not significant. Therefore, we will keep accepting the null hypothesis. That's like too many words here. So go back to the framework. Okay. So what we observed the right-hand side, he was correct 8 out of 10, and which can happen with 5.5% of the chance if we accept that he doesn't know the wine, or if we accept the null hypothesis is correct. Okay, and then hey, 5.5%, that's actually pretty, that can happen. Like, it's like maybe 1 in 20 times. So I don't think it's that much of the significant. Then we can say, well, so that means this left-hand side, the theory, the world theory, can explain what we are seeing. Yes, I know he was correct 8 times, which sounds like kind of a lot, but based on the random guess model, that can happen within a reasonable chance. Therefore, we don't have to change the hypothesis. We can still keep going with the hypothesis, which is a null hypothesis, that is, he doesn't know the wine. So we're going to keep accepting this hypothesis. That means the conclusion we have, the right-hand side top, is he doesn't know the wine. Sorry, even though you did a good job, 8 times 10, like I would be like, hey, wow, this guy's great. If you're at the party, like I would be like, yeah, it's great. I mean, if you're at the party, like you start coming up with like 5.5% or something like that, everybody leave your party, or at least leave you. So I don't recommend, but in the world of statistics. And then here, like you can argue, hey, that's too small of the data, just a 10. Are you kidding? Like you got to test a bunch, like 100 or 1,000. Well, you know, I just wanted to make sure he's not going to get sent to the hospital, so that I stopped at 10. But yes, you're right. You know, there's something about the volume of the data that's actually very important. And also what's the variance in the data. So there are many other things to come in this hypothesis testing as the key factors. But basically in this seminar, I just wanted to establish the sort of like a basic idea, like how this hypothesis works, why we do this, why we use the language that we have, such as null hypothesis, alternative hypothesis, that kind of stuff. So, and there are many types of hypothesis tests. We basically cover only the logic behind hypothesis test, or the framework of it. But the particular tests, for example, in exploratory, you can do like t-test, ANOVA, chi-square, normality test, Wilcoxon, classical Wallis, and so on. And even you don't see under the analytics view, you can always run the R command to do, you know, whatever the things you have on your plate with R, do the testing. And then like once you, for example, run the, let's say the t-test, and then you see this p-value, the one like we saw today's seminar. And then, but basically though, there are many, among many hypothesis tests, these are the ones like usually use, often used in the, you know, especially in the world of science and in the world of business. So most of the time, like what you want to do is basically like you see the difference by using a bar chart or line chart, whatever that could be, like you see the difference. And then that's the kind of beginning. Like basically, is that difference is a significant difference or just a random chance, like you saw, maybe like it just, you know, can be explained by the variability of the probability, right? So that's where you want to bring this hypothesis test. And if that target variable, the interest, the variable of your interest is numerical. For example, if you're testing like a number of clicks, sales numbers, or income or something like that, those are numerical. Then you want to do the t-test and ANOVA and so on. On the other hand, if you're seeing is maybe the conversion rate, something about the rate, or maybe like a attrition rate, or you know, cancel rate, or something like that, some kind of rate thing, which is basically the categorical or logical, the true or false type of data, then you want to bring in a chi-square test. It doesn't have to be rate. I mean, it doesn't have to be true or false. It can be like ABC, and what's the, you know, percentage difference among them. That also can be going to right-hand side, and a chi-square test can be used. And then from the next week's seminar, I'm going to start going one by one. So from t-test, ANOVA, and other like Wilcoxon classical Wallis, and then eventually the chi-square test. Okay, so that's for the stay tuned topics. Okay. And that's it for today. So as you saw, like basically today, I wanted to basically set the foundation of like what the hypothesis test is, like how you think about the hypothesis test, because it's a lot of kind of, if you're not familiar with it, if you're new to this thing, that's new to statistics, and then it's really confusing things. Like it took me a long time for me to understand what the hell is this hypothesis testing. So I just wanted to make the kind of a basic thing first, and then start getting to more actual or like a particular method of the hypothesis test. Okay, so that's it for today. So as always, if you go to our website, exploratory.io, you can see an online seminar link under that, and then you can see all the past seminar, especially like if this whole probability thing, it might have confused you in that case, like I recommend you to take a look at the Introduction to Probability seminar. There's a recording here as well. And also you can see what's coming from the next week as well. And also, if you are exploratory users, don't forget, go check under the Learn, go to the how-to tutorials and how-to video, and you can find a lot of sort of step-by-step guidance as well. Okay, and other than that, so my email address is kan@exploratory.io. If you have any questions, feel free to reach out to me. And also, we have the Twitter account, Exploratory Data. So if you you can follow, please follow, and we announce like this type of seminar information, new features of product, or any information about the exploratory. Okay. Again, thank you so much for joining today. Then at this point, I'd like to open up the questions if you have.